So, good afternoon, ma'am. My name is Bam CJ Manalo Balian from BSMAR 82 Delta. I will explain the relationship of pressure, temperature, and enthalpy in this Mollier diagram of R22 refrigerant. First, before answering these questions, these given questions, we first need to understand what this diagram means, what these lines means. This horizontal line, broken line, is the constant pressure, the constant bar. We can say it is labeled as bar. While the vertical or the from bottom to top, the broken line from bottom to top is the constant temperature. It is colored as pink, labeled as pink here. We can see the degrees Celsius, and this this line, the important line, this is the saturation curve. This one, the saturation curve. Inside the saturation curve is what we call the vapor region. Here I labeled it vapor region, and this one is liquid region, while this one is superheat region. So now, how did I get this kind of lines? How did I do that? First, we use the given of the refrigerant R here. We use the given of the refrigerant R22. So we will go back to the given here. So the given is the condensing temperature is 34 degrees Celsius. The condensing temperature is 34 degrees Celsius. The evaporating temperature is negative 15 degrees Celsius. While the discharge temperature, or the T2, let's say the T2 be the discharge temperature or the temperature output of the compressor is 70 degrees Celsius. So in order to get the line of this condensing temperature or 34 and evaporating temperature negative 15, we just follow the diagram. We need to look at the diagram using our eyes to get that 34 and make a horizontal line. So the condensing temperature is 34 degrees Celsius. Here I already labeled it as 34, so we get the straight line, just use the roller to get the 34 degrees Celsius, while the evaporating or the evaporator side is negative 15. That's how we get this line, this two line, the very important to make a trapezoidal system or cycle. Next is we answer the question number 2. Determine from the diagram the high and low side operating pressure. So the high side, of course, is the condensing side, the pressure. We say that the pressure in this high side is around 13.5 bar. Very precise, not accurate as in, but a precise one. Calibrating a precise answer. I calibrated it in a precise way. It is 13.5 bar, not Pascal, because the given is in bar, not in Pascal. While the low side operating temperature is around 2.9 bar. I calibrated it also around 2.9 only. 2.9 bar. I say around because I am not very accurate but precise only. So we already answered the B. So let's proceed to letter C. So the heat rejected by the condenser. What do you mean by heat rejected by the condenser? This C is, we calculate the enthalpy or the energy of the condenser from its input to output. So we cannot calculate the output over input in this one, or in let's say in C we cannot calculate, we cannot calculate the input over the output on this one. Output over the input, I mean, because it will give us negative answer. There is no such thing as negative energy. For mathematical equation, for precise mathematical equation, we need to get the answer as positive. So we calculate it as here. So H2 minus H3, or it is the input of the condenser subtracted to its output. So H2 minus H3, of course. 444 minus 229 is equals to 215 kilojoules per kilogram. We get the heat rejected in the condenser. Now, we answer the letter D, the discharge temperature. The discharge temperature is the temperature or the output temperature of the compressor. It is the discharge temperature in that region. So the given discharge temperature is 70. Yes, 70 degrees Celsius or the T2. That is the discharge temperature. So we already get the heat rejected by the condenser. We get that calculation, and we also get the points in the TA plus superheat, the T1, T3 in the A. We already get that. We just subtracted the evaporating temperature plus superheat. We get the T1, and in order to calculate the T3, the subcooled or the input of the expansion valve, the T3, its enter point is, we use the condensing temperature. Of course, it is in the condensing region, subtracted by the subcooled temperature. We will get the 24 degrees Celsius, the T3. So we can now point out the dots here, forming 3 dots. This is the discharge. This is the discharge, the T1, the T3, and the T4. So in order to get the T4, we just draw the horizontal vertical line along T3. Now this point we will make a broken line in order to get the precise enthalpy, not very accurate but precise only enthalpy. Putting all of that, we need to calculate the letter A, the total heat absorbed by the evaporator. So we will look at the evaporator side or the evaporator component. Meaning, in order to calculate the heat of this, we just need to subtract we just need to subtract its output over the input as usual. The output temperature of the evaporator subtracted by its input. So we can use the H1 minus H4. We will get that answer of 177 kilojoules per kilogram. Just simple as that. So work of the compressor, letter F. How to answer the work of the compressor? Just like calculating the heat of this, the total heat absorbed and total heat absorbed and total heat rejected, we just use this in the work of the compressor. We just subtract its output over input as usual again. So we use the H2 minus H1. Oh yes, H2 minus H1. We get 38 kilojoules per kilogram. So in order to calculate everything, we don't need to memorize the formula, but we need to understand how this diagram works. We need to subay the arrows. Like you just calculate the output over input. We give us the verdict answer we want. Just subtract the output over the input, just like in automation, just like in any engineering. We get that answer what we want. If we want to calibrate what's happening inside that 2 points, from this point to that point, we just subtract its output over the input. If we want to calculate how efficient is it, we just subtract. We just divide that. We just subtract. Divide the output over the input, multiply to 100. We get how efficient the system is. So going back to the topic, the last question is what is the quality of refrigerant entering the evaporator or evaporator? The quality of refrigerant entering the evaporator and liquid percent and vapor percent. So in order to calculate the vapor, we just set this T4 here. We look at point of it in the vapor region. Now this broken line, this inside the vapor region, this broken line, in this point we just look at what percent is entering in the evaporator, because this is the input of the evaporator. This point, this T4 is the input of the evaporator. As you can see, evaporator output, input. So the question is, what is the quality of refrigerant entering the evaporator? So we look at this point, because this is the input of the evaporator. So as we can see, it is around 0.2 kapin lapas. So I use the 22% vapor. So in order to get the liquid, we just subtract the 100% of the system, subtract the 100% of the liquid, subtract by the 22% of the vapor, we get that 78% liquid. So that's how we solve it.